Now we're touching now on what happens when you mix two things together. We talked about precipitation reactions. We had a solubility table that you could look at to see if you did happen to mix together some ions in solution and you could get a possible combination, what could come about because of that. Sometimes nothing will happen. You won't see anything happen, and those ions just stay dissolved, and we would consider that a soluble situation. Yes? No, I'll give it to you. Yep, I just want you to know how to use it. Okay? All right, the question was, do you have to memorize the solubility table on the test? And the answer is a resounding no. Okay? I'll give you that table. You just got to know how to use it. Because there's plenty of other stuff I can ask you that's harder than that. So. All right, so take this for example. If you mix together, back a couple slides, sodium iodide and sodium chloride in aqueous form, those ions are coming together. What new possible combinations could occur? Represented over there. Now the question now is, okay, first of all, is the equation balanced? Because we have to keep that in mind now, and it is in this case. But in addition to that, I've got to be able to give me as much information as I can. You need to give me as much information as possible regarding, what all you can tell me with this equation. You can tell me not only what you mix together and what ratio the atoms are to one another, but you can also tell me how many of each thing, like 2 of those or 1 of those. In this case, it's a 1-to-1 that you've mixed together. That tells me that. Tells me the possible products that could form. But as long as you leave this as aqueous, I know that those are just possible products, because what that tells me, if something's an aqueous solution, they're just floating around as ions. They're not really stuck together. However, if that was a solid, then you'd have to indicate as such, and I would know that that's some sort of precipitate. Or if it was a gas, I'd know that something bubbled out. And there was a gas evolution from that. In this case, the possible products are KCl and NaI, okay, are either one of those an insoluble product that would form a solid. If you look at your solubility rules, you will find that anything containing sodium and potassium are always soluble. So both of those would remain an aqueous solution. Okay, so this is already, what this is saying is, how do you predict the products of a precipitation reaction? That's everything that we just said. You've got to figure out what ions are present, how they can rearrange themselves, and then look at the table to see if that would give you something that would be considered a precipitate, something that's insoluble. Okay? You got to make sure you balance the equation if you're ever writing these as well. So, this one says, let's go back one. When an aqueous solution of sodium carbonate, so you got to know how to write sodium carbonate, is added to an aqueous solution of copper 2 chloride, a white solid forms. So what you should be able to tell me then is, give me an equation that expresses what you see here and tell me what that white solid is. Okay? If you mix these two things together, you see something happen, you don't have to ask me what it is. You should know now. Look at the ions involved, compare that with the solubility table, and figure out what it is. Okay? So, first of all, we've got to know how to write, in order to even come up with this equation, we've got to know how to write sodium carbonate in its formula form and copper 2 chloride. So the formula for sodium carbonate is comprised of sodium and a carbonate ion. Sodium is what? Na positive, right? Coming together with a carbonate ion, which is what? CO3 with a 2 negative. So how many sodiums do I need to balance that out? 2. So it would be Na2CO3. That's sodium carbonate. Copper 2 chloride. Remind me, what does that number 2 mean? The charge of what? Copper. It would be the charge associated with that copper ion. Because it's a transition metal, it can vary. In this case, it's specifying which one it is. So copper 2 means I have a Cu2 positive. What's chloride? What's the charge? -1, right? So if I'm bringing a Cu2 positive in with the Cl negative, how would I write that formula? CuCl2. Good. All right. Now it's a matter of what is this solid precipitate that forms, so we can figure that out. So here's what we know so far. I tell you it's aqueous solutions, so you're able to bring in these ions all separate from one another. They were stuck together first in solid form, but when you dropped them in water and dissolved them, now you actually have an aqueous solution, so you've pulled apart those ions. Water has dissolved them, and they're all spread out, and they can interact with each other now. Okay, what are the possible combinations here before we look down, before we go any further? Remember, only positives and negatives can come together, right, in the equations that we're dealing with here. So if that's the case, what from over here can go with what from over here? Okay, sodium can come together with chloride ions, okay, and copper could come together with carbonate ions. So let's see which of those might be a possibility. We've got to go ahead and write them. Here's our ions, okay. We've broken it down. We've already done this in our head because we put those together to get that, but realize that's what's actually floating around in here. Okay. Exchange them like you just did. In other words, put the carbonate with the copper and switch these. Switch this guy and this guy. Just loop them back around and switch them places, and they swap partners. Just do that. Okay. When you do, you position them next to each other in this manner, and we know that when Na and Cl come together, Na atoms are 1 positive, Cl ions are 1 negative, so it's just NaCl when they come together. That's the way you would write it. Here, if you have copper 2 ions floating around, and you have carbonate ions floating around, you know that that's a 2 positive, that's a 2 negative. They balance each other out. They just come together in a 1-to-1 relationship. So CuCO3 is how you'd write copper 2 carbonate. Okay. So then what we can do is write it out completely now in full form, not just all the ions present. Write it all the way out. We've got sodium carbonate reacting with copper 2 chloride, and you told me the possibilities were sodium chloride, that's how you would write sodium chloride, and copper 2 carbonate. There's that. So the next question is it balanced? Let's take a look. The sodiums have 2 over here and 1 over here, right? So what do we need to do? Okay, put a 2 in front of there. We've got 2 NAs now. Okay, so let's see how we've affected it. 2 sodiums there. If we put a 2 there, we'll have 2 sodiums there. We have 1 carbonate group. Now, I told you before, probably what you want to try to do if you can, instead of doing 1 C and then looking for C's over there, and just oxygen here and looking at oxygen over there, if you can get away with it, just look at the carbonate group as a whole. It's going to be easier to keep track of. So you see like 1 carbonate ion here, right? There's 1 carbonate ion over there, so that's good. All right, copper, 1 over here, 1 over there, we're good there. 2 Cl's here. Remember, we just put a 2 in front of that, so that fixed that, so we're good. All we need to do is put a 2 in front of that, and everything's balanced out. All right, so that step's over. All right, now, the question is, I know this is aqueous, I know this is aqueous. One or both of these or something has to be a solid because you've observed that a white solid forms. So how do you deal with that? We got to figure it out. Well, that should be easy to you because what do you know about salt? It's soluble. It dissolves. We've all made saltwater solutions before. So even without checking, you know that it's not going to be NaCl. Okay? You cannot, like I said, it's very, very, very difficult to mix 2 things together and get sodium chloride as a solid. So any form of sodium tied up in a solid form in a precipitate. It's very, very hard to do. So in this case, what you will see is if you look up, though, if you don't just pick that up and just look at your your solubility table, you'll see that anything bonding with Na is soluble, so that's not going to be it. Your carbonates are usually always insoluble, and copper's no exception to that, so you would look on the table and you would find that. That means the precipitate that you see in this reaction must be copper 2 carbonate, and you can explain that. So how you would indicate that in your equation, of course, is write a solid after the copper 2 carbonate, and write aqueous after NaCl because it's soluble, it's still dissolved. Okay? All right, now, ionic equations you've pretty much already did these when we did the last lab. Okay? As long as you can understand what we just did, ionic equations are the same thing except you involve just the ions as opposed to all the stuff stuck together. That's it. Okay, so ionic equations are those which describe the chemicals put into water, and the product molecules are called molecular equations. So in other words, if I bust this up, and instead of writing this all together, and instead I separated out K positive, OH negative, Mg2 positive, NO3 negative, and wrote them out separately, then I've got an ionic equation as opposed to a molecular equation. Molecular equation means I stick together what's probably going to be stuck together. Keep it, instead of separating them out, put them all together. So, let me show you some examples here. You already know this. I've already talked about this. So, in this case, now I want you to realize something in terms of keeping track of numbers. Okay? If I ask you to write this in ionic equation form, what I'm basically asking you for is give me all the ions that are floating around in this situation. So if I have 2 potassium hydroxide molecules, granted it's an aqueous solution, but let's say they were together. Okay? How many potassiums are there? How many hydroxides? 2, right? So don't forget that. So down here you would actually write 2 potassium ions in aqueous solution plus 2 hydroxide ions. I've separated them out, but remember that 2 goes with everything behind it. So I've got to put the 2 down here with this as well. 2 hydroxides in aqueous solution. I've got MgNO3, 2. That means there's 2 nitrate groups with that magnesium. Remember how we got that. Magnesium forms what charge? 2 positive, right? And nitrate, each one has a 1 negative, so that's why there's 2 nitrate groups there to balance that out. So I've got 1 magnesium with the 2 positive charge in aqueous solution. Looks like I've got 2 nitrate groups right here. So I've got to indicate that here. Now, you might want to just put parentheses around that. That might be what you are compelled to do. Put parentheses here and put the 2 after that, but that's just not the way we do this. Okay? You would put a 2 in front, even though the 2's after it right here, because this is just only affecting this. So 2 nitrate groups there. What will that yield? This is more specific than this, just because it takes this. I say it's an aqueous solution here. This shows me that it's an aqueous solution. What I've done here is take 2 potassium nitrates. That means there's 2 potassiums present, okay, in aqueous solution. 2 nitrates present, 2 nitrate ions present in aqueous solution. However, you can't separate this out because these are no longer separate ions. Magnesium hydroxide is a solid that forms in this case. It's stuck together. So what does not exist there are floating ions. They're actually locked up with each other to form that solid precipitate. That's why these are not separated. Okay? That remains a solid. That's the only difference. You can see that they're just 2 different ways to say the same thing. Okay? Now, we talked about this already. In this reaction, we can now see when I talked about spectator ions, when we did net-ionic equations with our precipitate lab, the spectator ions are the ions that are involved in this entire thing that don't really do anything. They just watch, hence the term spectator. If you're mixing all this together, potassium hydroxide allows you these ions. Magnesium nitrate allows you these ions. Realize that the only ones that actually reacted to form a solid was the hydroxide and the magnesium. In other words, this guy, as shown over here, stayed the same. The potassium over here stayed the same. They just watched. However they were like over here, they're still that way on the other side, so they've just watched what happens. They didn't really participate. So we call those spectator ions. Okay? So if you were writing what's called a net-ionic reaction, that means not gross. After everything's said and done, what really only mattered in this situation? The net-ionic reaction would just be whatever helped make this form right here. And that would be that plus that. Those 2 things together to give you that would be the net reaction that occurred out of this. Okay? Spectators. So the net-ionic equation would be written there. Okay? 2 hydroxides come together with 1 magnesium to make MgOH2, to make a magnesium hydroxide. That would be the net-ionic equation. So that's what's called an ionic equation. This is a net-ionic equation. And going back to before, when everything was written out, all stuck together, that's just called a molecular equation. Okay? The difference between them. All right, now in the last chapter of the semester, we will be discussing acids and bases in more detail. Okay? But for now, I'm just going to mention them because we are discussing the different types of chemical reactions, and I'm going to mention them, and then we'll get to the specifics later. But bottom line, acid-base reactions, when you're taking an acid, something that's called an acid and something that's called a base, and bringing them together, basically what that also can be called is a neutralization reaction. They work against each other. What you will find is that acids like to give off hydrogen ions. That's what makes them dangerous, and they're very reactive. When they drop off their hydrogen ions, those hydrogen ions go around and react with things. Bases, on the other hand, like to nab and steal hydrogen ions. They're just as dangerous. So when you mix the 2 together, this one's got what this one wants, and they just sort of neutralize each other. They sort of fizzle out as a result of that. However, if you realize that if you get an acid on your skin, the reason that it burns so bad is because you're going to release a whole bunch of hydrogen, and that hydrogen is going to go out and react with all the chemicals that are in your skin. Okay? A base will do the same thing, except in reverse. If you get a strong base on you, like sodium hydroxide or whatever, it's going to hurt too, because instead of donating all those hydrogens to pull apart the tissue, it's going to actually just pull apart the hydrogens from the tissue itself. So either way, you've got tissue destruction. It's a matter of whether it's donating the hydrogens to do that, or whether it's taking hydrogens from the tissue itself. Same principle, it's just sort of in opposite directions. They work antagonistically to one another, acids and bases. Okay, so when you have an acid, what you will see is, like, for example, a common way to recognize acids is, well, like HCl. We know the hydrochloric acid is an acid. HCl, and the reason that it's so dangerous is because what it will do is when it's in aqueous solution, will separate like that and donate that hydrogen ion. A very strong base is sodium hydroxide, NaOH. What it will do is the same thing in an aqueous solution. It will separate right there. And what will happen is, like, if you mix these two things together like this, is this hydrogen will react with this hydroxide. Guess what you get? You get a little high quality H2O. Okay? You get water, which is certainly not dangerous, right? This is why it's called a neutralization reaction. When they come together, they neutralize the potential from each other. Okay? Funny. All right. So one of the things that you will find in chemistry, there's a rule of thumb that we can follow. And you keep this in mind. Don't forget this, because you'll need it later. Acid plus base will always give you what? Salt and water. I'll show you what I mean in particular. The water we know. Okay? Take a look at what I just drew. If I go back, I don't know if I covered it up or what, but it looks like it's gone. Let's do this again. Acid plus base, HCl. So all I care about from that's the hydrogen, okay, that comes off of that. But I've got HCl that ionizes in solution. I've got NaOH, right? And when it dissolves, that's what you get, Na and OH negative. And you said these guys came together to form water, and you're right. That's the neutralization process. Look what these can form here. Sodium chloride, right? So what you will get is, if you take muriatic acid from Lowe's, go to down to the like the masonry and the sidewalk area and that kind of stuff. Muriatic acid is hydrochloric acid. Okay, it's a common name for it. And then go get some Drano. Well, it depends. You have to look on the bottle. Sometimes it's hydrochloric acid, sometimes it's sodium hydroxide. You can get drain cleaner that's sodium hydroxide as well. So go to the drain cleaner section and get some drain cleaner that's actually sodium hydroxide, if you read the ingredients. Assuming that there's the same amount of both and they're both the same strength. You know, I have to show you how to calculate that, but assume the theory here. Mix it together, what you would actually get is salt water by the time that you're done. Now, I don't know if you're good enough to want to drink that or not. How confident you are in yourself, but it is certainly possible, okay, to just make salt water from this reaction. It neutralizes itself. Okay, so acid plus base will give you salt and water because of what you see here. Okay, what was group 1 on the periodic table called? Alkali metals. What was group 2 called? Alkaline earth metals. What does the word alkali mean? Anybody know? Basic. You'll find that those metals like to form bases like NaOH, sodium hydroxide, calcium hydroxide, potassium hydroxide. That's how they get their name. Alkali and alkaline metals, that kind of stuff. Okay. Take this example. What's HNO3? Good. Nitric acid. Good. Nitric acid reacting with, what's this? Good. Calcium hydroxide yields. And, yeah, don't think too much about that one. You're right. Okay, good. Now, this is already balanced, but you would obviously, anytime you see an equation, that should automatically pop in your head. Make sure before I do anything that I'm working with the balanced equation. Okay, so in this case, what the net ionic equation would be. This will be important. You need to understand this. Up until now, the net ionic equation had to do with formation of solids. Well, what you will see is the net ionic equation actually is the equation for the formation of anything, whether it's a liquid, solid, or gas. That's still part of that's the net ionic equation. In this case, what forms, of course, is not solid water. Ice doesn't form when you mix these things together. But water molecules do form. So liquid water molecules form. You don't have aqueous solutions of water. It's like saying you dissolve water in water. That doesn't make any sense. Okay? So if water forms, it's going to be in what's called liquid form. So since there's a liquid that forms, in this case, we said the hydrogen is going to react with the hydroxides to form water, right? That's where that came from. The salt, remember what a salt is. A salt is anything, any ionic compound, it's got a metal and a nonmetal, any ionic compound that can dissolve, we call it a salt. Okay? So the hydrogen, the hydroxides make water. The nitrate and the calcium make a salt, calcium nitrate salt. So acid plus base gives us salt and water. Okay? What is the net ionic equation? The hydrogen ions come from here. The hydroxide ions come from here because that's what made that water. Okay? So that's what you see down here. Yeah.
Also, salt, why is it aqueous?
Because it's still an aqueous solution. It's dissolved. Okay? The only time we do net ionic equations is for solid, liquids, or gases. Anything that's not just suspended ions in solution. Solid, liquids, or gases. Yeah. Anything that's, like I said, if it's an aqueous solution, just realize what that means. It means that they're really not stuck together. It just shows you a possibility. But by putting aqueous solution, really tells you that they're actually spread apart from each other and floating around in there. They're not sticking together at all. Okay, that's assuming. Now make sure you understand too, this last disclaimer I throw on here. It says that's only as long as the salt that forms is actually soluble in water, right? Because if this was something that formed that happened to be insoluble, you would actually have, the net ionic equation would be two of them. You'd have this one for water and whatever it was for the salt, if it was a solid. But in this case, calcium nitrate, all nitrates are going to be soluble. A lot to think of. Got to keep it straight in your head. All right, so here we go. Write the molecular, ionic, and net ionic equation for the reaction of aqueous nitric acid with aqueous calcium hydroxide. Well, that's what we just saw, but now I want you to break it down and write down everything about it. Okay? So, nitric acid, quick, what is it without looking? HNO3, good. Okay? Calcium hydroxide, what is it? OH in parentheses with the 2, because each hydroxide is 1 negative, the calcium is 2 positive. Good. So there we go. Now what are my possible combinations? Well, H2O coming from this and calcium nitrate. Those are my possibilities. Okay, so this shows my ions. Just you do this in your head. You can separate this in your head. This just wrote it out for you. Okay, exchange the ions, combine the new things together. What can you come up with? And you said already H2O. H2O is a liquid. Okay, so you can actually put those together. And also calcium nitrate, but you'll see that that's insoluble. Or sorry, you'll see that that's soluble. It remains in aqueous solution. Okay, so what does that mean? That means that we can finish the right side of our equation. So the first part said write the molecular. So I'm looking for the molecular equation. Molecules, not just individual ions. So I have nitric acid in aqueous solution. Mixing in with it calcium hydroxide in aqueous solution. What comes about? The possibilities are calcium nitrate and water. Notice that I don't have anything labeled after calcium nitrate yet because I've got to look and make sure, unless I'm doing this experiment. If I do it and nothing forms, I know that this is true, but if I'm just looking at it on paper and looking at it from a theoretical point, I've got to check and see if that's going to be soluble or insoluble. Okay? What do you know about nitrates? Always soluble. Okay? All right, so there's my molecular equation. I've got to balance it. Okay? Looks like I didn't have it here, but realize what we had to have done. If we look up here, there are 1 hydrogen here. There's 2 hydrogens there, right? So we got a problem there. Take just a general inventory. It looks like there's a 1 nitrate group here, 2 nitrate groups there, 1 calcium, 2 hydroxides. I'll tell you what will help, I think, whenever you're trying to balance equations for water. Okay? Instead of writing it as H2O, write it as HOH. If you write it as HOH, it's easier to keep track of stuff. I'll show you what I mean. You know that the hydrogen and the hydroxide came together to make it, right? Well, what you're able to do then is keep track of things. Like you've got your two hydroxides here, and you've only got one hydroxide there. See what I mean? If I write it HOH, it's easier to visualize that as opposed to writing it H2O. Whatever. I mean, you can do whatever you want. I'm just saying I think this would help. One hydrogen here, that one hydrogen there. So, how would I do that? I'd have to put like a 2 in front of that one, right? If I put a 2 in front of that, I've got 2 hydroxides over there and 2 hydroxides over here, and I would have, not counting, since I counted that H with the hydroxide, I can't count it again. Okay, so that would be 1 hydrogen here, 1 hydrogen here. That looks good. So, what do we do next? Do I need to do anything? What? Okay, so we put a 2 where then? Over here. So if I put a 2 here, looks like I already got the answer down here, don't I? I guess there's no point showing you that. As you can see from the answer already on the screen, if we put a 2 here and a 2 over there, that'll balance everything out. Okay? I don't need to go over balancing again. You know how to do that. It just takes practice. You know the theory behind it. You've got to figure out a way to make that happen yourself. Anyways, balance the equation. Okay? All right. Now, you can look up on the table and write that in at any point as far as what calcium nitrate would be. And it is soluble, so you can, or insoluble. Soluble, sorry. So write it accordingly. Okay? So it will be aqueous solution. All right, so there is our full molecular equation for this particular reaction. Easy, right? Piece of cake. It's not too bad. It could be worse. Next step, ionic. It's all downhill from here, right? You've got the molecular equation. All you got to do now is bust it up into ions and tell me how many of each ion are present. Now, the only thing that you're not going to include in your ionic equation, the only thing that you're not going to separate is, in this case, water, because it was a liquid. The rest of them, anything that's aqueous, that's what you're going to be putting in as ions, because they're actually dissolved ions. If you had a solid, a gas, or a liquid, you're going to keep it together, because it's not ionized in the final product. So in this case, if I had 2 nitric acids from the previous equation, that means I had 2 hydrogens, 2 nitrate groups. It shows it right here. In the previous, it said CaOH in parentheses 2. I had a calcium hydroxide. That was an aqueous solution. So that means I have a calcium ion and 2 hydroxide ions, as you can see here. I've just spread it out. We also said that this was soluble. So if I have Ca in parentheses NO3 followed by a 2, I've got calcium nitrate, 1 calcium, 2 nitrate ions. So that's an aqueous solution. That's soluble. The only thing that's not then is this water in liquid form. Okay? So that would be the ionic equation. What would be, without looking, what would be the net ionic equation? Why? What do I use? You're right. What do I use for the net ionic equation? Only those ions that were what? Not aqueous. Only the ones that made something. I include the aqueous ions in the total ionic equation. I said the net ionic equation. When I cancel out everything that's spectators and get rid of everything that wasn't involved, I want to look at those ions that were only specifically made something from this reaction. That is the net ionic equation. So in this that you see, look, you had calcium ions over here. On the other side of the equation, you still got calcium ions. They didn't even react with anything. I've got nitrate ions here, nitrate ions here. They didn't react with anything. They're spectators. The only thing that actually changed from the left to the right side of the equation was this guy. These guys here, these guys here came together to make water. So that's going to be what I'm going to use to write my net ionic equation. So I would write, in this case, 2 hydrogens in aqueous solution react with 2 hydroxides in aqueous solution to make 2 water molecules that are liquid. You think that is my final answer? That's right. If everything has 2's in front of it, If I have two of these, two of these, two of these, is that simplified? No. Get rid of those 2's, divide everything by 2, then you've got this. Okay, 1 to 1 to 1. That's the final net ionic equation for the formation of water. All right? You got to go through this. You'll have to review it. You also have reactions now, moving past acid-base reactions, what's called gas evolution reactions or gas evolving reactions. This is any gas that when you mix it, any reaction when it happens releases some sort of gas. Take this for example. Say you've got aqueous solution of potassium. How would I say that? Potassium what? Sulfide. With a D, sulfide. Potassium sulfide. And I'm reacting with it. What's this? Well, that seems logical that it would be hydrogen sulfate, but how would I actually name it? Well, what do I know if I have a hydrogen in front of it? It's an acid. So how do I name this acid? That's sulfuric acid. Okay? And when we name oxyacids, we look at it, it looks like some sort of ionic compound, but the difference is I don't have a metal, I have a hydrogen in the front. It's going to be an acid. So is it going to be the only thing that looks like this, polyatomic ion-wise, on your sheet was sulfate and sulfite. Okay? Sulfate is SO4, 2 negative, right? We said 8 ends with ic, ite ends with us, okay, in terms of acid. So this is sulfuric acid, carbonate acid. All right, so if I take potassium sulfide, mix it in with some sulfuric acid, what's going to happen? You're going to get a very effervescent reaction, something that's bubbling significantly. You will form a salt, potassium sulfate salt, that will remain dissolved in aqueous solution. Okay? However, you will also produce this gas, which you could name it 2 ways. There's 2 acceptable names, well, many more, but as far as what you would hear most commonly. Hydrogen sulfide, more particularly, people get away with calling it hydrogen sulfide. It should be dihydrogen sulfide. More specifically, it's actually an acid. Okay, but we can just call it. You don't get it called by its name. Sulfurous acid would be its name. It's not wrong. It's not sulfurous acid. Hydrosulfuric acid is what it would be called. But you can just call it dihydrogen sulfide. That's fine. Point being, though, it's a gas that has evolved. Stinks. This is that sulfur smell that you would like with rotting eggs and meat and that kind of stuff. This is the dihydrogen sulfide gas that would come off as a result from that. But anyways, if a gas has evolved, then it's a gas evolution reaction. Okay. If it says other reactions can be from a decomposition of one of the ion exchange products, and one of these things that had especially oxygen tied up in it into a gas and water. Look what I have here. If I take, should be 2 steps to this. Let's see. Yeah. If I actually take a salt of potassium sulfate and I have some sulfuric acid and I mix them together, that's a little bit different than what we had up here. This was just potassium sulfide. So when these came together, this gas formed. This is a different reaction. Your products, when you switch them around, are going to be something different. So if this hydrogen came in contact with this group, you would form sulfurous acid as a result, and potassium sulfate. How could this be a gas evolution reaction? Now, I don't expect you to memorize all these steps. You don't have to. Don't worry. I just want to point out something. Okay? You could still get a gas here because what you get with a lot of gas evolution reactions that have these polyatomic ions in them is intermediary products. This will form. Neither one of those are gases, but when they form, they then decompose. They can fall apart. And when they do, like for example, take this sulfurous acid. It likes to fall apart very easily into what's made up inside of it, which is H2O plus sulfur dioxide gas. That's like what you get when you burn coal. Sulfur dioxide gas is a pollutant, an environmental pollutant. When it goes, now realize this equation can go the other way. If we burn a lot of fossil fuels, we get some sulfur dioxide gas just from the impurities that are in our gasoline too whenever we drive our cars. When sulfur dioxide, and especially at energy plants and coal plants and that kind of stuff, when it's cranked out into the atmosphere, what you need to realize is this equation can go the other way too. What do you think happens when all that sulfur dioxide goes up and mixes in with the water vapor in the air? Acid rain. Okay, this is how it can happen. It goes back the other way. It forms this, and you get sulfurous acid, and it actually falls down as an aqueous solution in the raindrops as it falls down. So that's never good. Just so you know, if you've watched, what movie was it? Because there's two of them that are alike, Dante's Peak and what's the other one with Tommy Lee Jones in it? Volcanoes, that's the name of it. Well, which one? I think it was the one with Pierce Brosnan. That would have been Dante's Peak. The one where the grandma, she's trying to rescue the kids, and she gets in the lake, and she was walking through the lake, and like the lake has turned to acid, and it eats off her legs, or whatever. The theory behind that is certainly this. It's saying because when volcanoes erupt, there's tons of sulfur dioxide that gets spewed up into the atmosphere. And all that sulfur dioxide, everything's warm, so water vapor starts to condense and starts to get liquefied. You get to create this solution of sulfuric acid, basically. So acid rain is a byproduct of this volcanic eruption. But they made it a little bit more dramatic in saying that one of these lakes actually on the volcano turned into this giant lake of sulfuric acid that could eat your legs off. That's pushing it. You generally have to manufacture acid to get it that strong. Yeah, same principle. Same principle. Yeah. Lye is actually sodium hydroxide. It's a very strong base. Well, it has. I don't know all of the details on it, but I know that lye in its concentrated form, that's the lay term for sodium hydroxide. So if you have concentrated lye, you have a base, a very strong base, which is similar to an acid. So a very strong base will burn you, very much so. It will strip hydrogens away from the molecules that are in your tissue. I don't know if there's a neutralization reaction probably that goes along with that to try to eliminate the strength of that and knock it down. I don't know exactly how you make it. Now, when you have different, so you know where some of these gases can be evolved from. If you see something, some sort of metal with a sulfur atom attached to it, generally, and you're reacting it with an acid, this is where acids become very important because acids and bases do a very good job of evolving gases from equations because of their nature. But like anytime sulfur is present, this is probably the gas that's going to form if you're involving an acid. If you have a metal and a carbonate ion, guess what gas is trapped up in the carbonate ion? Well, it's obvious. CO2. So at some point along the line, you'll see that CO2 gets pulled out of that intermediary product. Okay? This doesn't decompose. It stays the same way it gets released. When this forms, this decomposes, and that's where the CO2 comes from. Okay? If you have SO3, guess what gas I just talked about that's trapped inside that? SO2, sulfur dioxide. So if this forms as an intermediary, which it would, it's going to decompose and release that from within it, SO2. In the case of anything with an ammonia ion, okay, if there's an ammonium ion, and it is allowed to react with an acid, what you'll get is NH4 will lose one of its hydrogens and give you ammonia, that really strong, you know what ammonia smells like. Okay? So these are some gas evolution reactions. Take a look at those equations. You can see how they came about. Okay? Potassium sulfide, hydrochloric acid, exchange those ions. What do you get? KCl, hydrogen sulfide gas. Potassium carbonate and hydrochloric acid. Exchange those. What do you get? KCl, and you get, you're going to get what your other product would be H and CO3s coming together. But what's going to happen is that's going to fall apart. It's going to fall apart into water and carbon dioxide. Okay? And so you just got to be able to recognize these types of reactions. You don't have to know all the steps necessarily. No, I'll be able to provide you with any charts that you need. What time is it? That's right. Okay. Now, how do you go about predicting some of these things? Like I just said, because I just kind of skimmed through that last chart. How do you predict the products of this gas evolution reaction? Because you're going to have to know how to do that. If you see bubbles start to happen, I want to know what those bubbles are and explain to me and justify why they're there. So you know how to exchange ions. You know what can bond with what in terms of positives and negatives. So that's what you need to do first. Check to see if any of those common things that I just showed you form. Is there a sulfur dioxide situation? Does it look like it's going to be a CO2 situation? Does it look like it's going to be a hydrogen sulfide situation? What's it going to be? Those are the most common. That's all we'll deal with in here. So there's plenty more, but we'll try to keep it as simple as we can just to get the process down. And if any products decompose, like if you have H2CO3, and you see that CO3 obviously has CO2 within it, realize that chances are, almost always, what you're going to do is when that falls apart, you're going to get that gas, CO2, and water. If H2SO3 does the same thing, pull out the SO2, what are you left with? An H2O behind. Okay, so you're going to get water and that gas. That's what's going to end up. Okay, so maybe there's an example here we can look at. When an aqueous solution of sodium sulfite is added to an aqueous solution of nitric acid, a gas evolves. I want to know what it is. Okay, you see it bubble. Explain to me why it is bubbling. I got to know what this is. What is the formula for sulfite? SO3, 2 negative. So how would I write sodium sulfite? How many sodiums would I need? 2. So Na2, SO3. That would be sodium sulfite. Nitric acid is what? How do I write nitric acid? H what? HNO3. Good. Okay, so I've got that far. We're dealing with aqueous solutions. Okay. Now I got to figure out what I can recombine and form on the other side. So there's my ions. I've just separated them. You did it in your head, but it doesn't matter. Let's exchange these products. And when I do, I will put the sodium with the nitrate, the hydrogen with the sulfite. Okay, and when I do that, I can rewrite it. I know that I'll need, looks like the charges work out here. That's a 1-to-1, so it'll just be NaNO3. What about this one? How many hydrogens will I need here? I'll need 2 of them, so when I write that out, okay. Now, I've written it out like it needs to be. Now I need to check to see if it's balanced. Is it balanced? No. Okay, I've got 2 sodiums over here, 1 sodium over here. If I put a 2 right here, I've got my sodiums balanced, but now I've got 2 nitrate groups, right? So what if I put a 2 here? It'll balance my hydrogens and my nitrate groups, and I'm done. Okay. So, look at this point. I don't know if I go to the next step of balancing this equation, but that's what you should do. My next question then is, I know that a gas evolved. The observation said that it did. You have to determine what this gas is. Are either one of those the gas? Is basically the question. As written, are either one of those the gas? Well, sodium nitrate is soluble in solution, right? It's a nitrate compound. It stays dissolved. What do you know about H2SO3? What is it? Well, okay, but first of all, it's an acid. What do you know about acids? Those are solutions, right? They're going to be dissolved as a solution. So probably as written, neither one of those are going to be the actual gas. Now, you will see that the gas will come out of that. Which one of those is the gas going to come out of? The acid. And what gas is it we're going to get? H2O is the water. We're going to get SO2, right? Sulfur dioxide is going to come out of it. Good. Okay. So does either one of these decompose? And the answer is yes, this one. And when you pull out an S and 2 of the O's, you're left with 2 H's and 1 of the O's. So that's where the water comes from. Okay? So that's this. So there's actually what is happening. That's how you would write this equation. These guys are coming together, right? You get sodium nitrate, and instead of writing this, you do one more step and show me what that breaks down into. And that's what you write over here. You write you write SO2 and H2O. Now, in this case, since it is a gas evolution reaction, I guess you probably want to hold off and balance until you've already figured all that out, but I guess you could do it either way. You might have to readjust. So it's best to hold off until I guess you're done writing the entire equation before you try to balance it. It's okay. You already balanced it once. You can do it again. Let's make sure you look. It looks like it's still the same. I don't know what we did different from the first one, but you can balance this equation. Okay, look at it. In this case, you had 2 sodiums here. We did that last time. We put a 2 there. And we also did it here too. So yeah, that's still, and that should make sense. It should still be the same because all you did was take that H2SO3 and separate those atoms out from each other. You didn't change the numbers of them, right? You just moved them out into H2O and SO2, so you shouldn't have affected your balanced equation anyways. So you can check here though. Okay, so we know that NaNO3 is soluble, so what do I write after it? Aqueous, okay. I know that H2O is going to be a liquid, right? So I've identified, and I know because of common knowledge, and you'll pick up on this, there's only a few of them really that we'll deal with. Sulfur dioxide is a pretty common gas. That's going to be my gas. That explains why I saw these bubbles when I mixed these two things together. Okay. Yes? No. Water comes before sulfur dioxide? No, it doesn't matter the order, as long as they're all there. Yeah. It matters whether or not it's on the right or left side, but it doesn't matter what order you put them in. Some other patterns. We've talked about these. We've talked about precipitation reactions. We've talked about acid-base reactions. We've talked about gas-evolving reactions. And in all of these, we've seen ions switch partners. Okay? There are also situations, and I don't expect you to understand all the details of this, but recognize it. Okay? There are also situations where instead of necessarily 2 ions exchanging places, you could have one atom here next to another atom here, and what you get is the exchange of electrons without ever actually forming anything as a result of that. That would still be considered a reaction if electrons move. Okay, let me show you what I mean. If there are atoms that transfer electrons from one to another, we consider that a reaction. It's different because you can't keep track of ionic movement, but you can realize, let me ask you this, how do you keep track of it? If electrons change from one atom to the next, how can I monitor that? What can I look for? Exactly, the charge. So in other words, if the charge changes from one side of the equation to the other, you can look and see by what it's bonded with, right? If the charge changes, then we call that type of reaction, even if it didn't switch partners. Okay? If it went from CuCl to CuCl2 to the other side of the equation, realize that charge must have changed. It went from a 1 positive to a 2 positive on the other side of the equation. That copper did. If that's the case, we call that type of reaction an oxidation-reduction reaction. Okay? It's a big fancy way of saying somebody gave off some electrons, somebody picked up some electrons. We call that oxidation-reduction. Okay? The difference in where you're going to see this is like rust on your car. That's an oxidation-reduction reaction. Generally, this does not involve 2 aqueous solutions being mixed together. It's sort of like a gas is on top of a solid or on top of a liquid, or a solid is dropped in a liquid, something like that, where you have different states of matter involved. Now, there's an easy way to remember this. Okay, you might want to jot this down. I can't remember if it's on here or not. Look and see. But it should say Leo goes grr on there somewhere. Okay, like Leo the lion. Leo goes grr. Lose electrons, you're oxidized. Okay? If you gain electrons, you're reduced. Oxidation-reduction happens together. If something is oxidized, something in turn must be reduced, and they form a pair. Okay? All right, let's take a look. Anything that gains electrons is reduced. Now, why do we use the word reduced? How does that make sense if it's gaining something? What is it that's reduced, do you think? The charge. If you go from a -1 and you gain an electron, what does your charge become? More negative. -2. It's -2 on the number line is a lower, more reduced value than a -1, right? That's how you get its name, reduction. It's gaining electrons and in so doing becoming more negative in charge, reducing its overall total value, okay, in terms of the number line. So Leo goes grr. Lose electrons oxidized, gains electrons reduced. You can't have one without the other. All right. So if, let's say, a metal reacts with a nonmetal, okay? You have like a room temperature situation. It's reacting, say, metal, letting it come in contact with the environment, like a piece of iron. It's moist, it's humid, it's a lot of oxygen in the air, that kind of stuff, oxygen in the water molecules. You'll get rust formation as a result of that. In that case, what will happen is, what charges, put it all together here, what charges do metals like to form? Positive or negative charges? Positive charges. How do you form a positive charge? What do you think you have to do? You lose your electrons, right? How do you nonmetals like to form negative charges. How do you form a negative charge? You gain electrons. So guess what? Whenever a metal comes in solid metal comes in contact with some sort of situation where there's nonmetals, you get an oxidation-reduction reaction. It's another way to look at what an ionic compound is, because iron in that case would give up its electrons. So it loses its electrons. So what do we call it? If it loses its electrons, it's oxidized. Let's say it was oxygen over here. There's a reason I'm picking oxygen. Okay? If oxygen is over here and it takes those electrons, it gained electrons, right? So it is reduced. So how did you get the word oxidation out of this? Because originally, when it studied, it was testing the effects of oxygen on metals. Okay? So what oxygen could do, like the other nonmetals, is come in and pull electrons away from it. So if a metal reacted with oxygen and oxygen pulled away its electrons, it was said to be oxidized. Well, then you figure out that not only oxygen can do that, but sulfur can do that, chlorine can do that, other things can do that, but they left the name. Okay, it's still called oxidation, even though it was based upon the results of oxygen. Okay? So if it loses electrons, it becomes oxidized. The iron became oxidized, as if oxygen came in and grabbed it. Okay? All right. Now let's take a look at an example. Take this. Say you have a piece of solid sodium, and you drop it into a container with a whole bunch of chlorine gas. Remember what color chlorine gas was? Greenish yellow kind of color. Let bleach set around long enough, and you'll see what I mean. Sort of gets a yellow hue to it, kind of a yellow stain, that kind of thing. Sodium hypochlorite, which dissolves into chlorous acid, which is bleach, but I guess you don't care. Take solid sodium, let it react with chlorine gas. So what you would not want to do then is well, it would be violent, but it would be very heat-releasing, I guess. Never mind. Take sodium, chlorine gas. When they come together, they form sodium chloride, certainly. Okay, and that's easy. You can see that. But the difference is, and what's different about this, is that this was not in an aqueous solution. This was not already in a positive form, right? This was elemental sodium. It's just a lump of solid sodium all by itself. Same thing here. This is neutrally charged individual little molecules of two chlorine ions stuck together. So this is a little bit different than what we looked at before. And we don't have aqueous solutions. So they can still interact, though. And when they do, the way that they're going to interact, instead of just exchanging ions, there's no ions present, one will actually come into contact with the other and either take or give electrons as a result of that interaction. Okay, so let's look at the other side of the equation. What is the charge of this sodium sitting here? As it is. It's 0, right? It's not ionized. It's charge neutral. What about these guys? No charge either. These are charge neutral because they're not. The only way they can have a charge is if they're stuck with something, or if you write it as aqueous solution. Written as it is, this is solid sodium. This is gaseous chlorine. They're just non-charged molecules that these guys are, two of them are stuck together. This is just a lump of solid sodium atoms all sort of gravitated towards one another. I'll explain that a little bit later. Okay, so on this side of the equation, however, I got the formation of sodium chloride. Are there ions on the right side of the equation that are involved in forming whatever it is that's there? Yes. The reason that sodium chloride are stuck together is because sodium has a positive charge, chloride has a negative charge. So what happened? The reason sodium has a positive charge is, guess what? What happened to it? How did it get its positive charge? It lost its electron to chloride ion. Chloride ion became negatively charged because it gained that one electron that sodium gave up. I can look over here on the right side of the equation and see that this came from an ion that's one positive, as it is here. This is an ion stuck to it that, if separated, would be a 1 negative, right? So I went from 0 to 1 positive for the sodium. Was that oxidized or was it reduced? Did it lose electrons or gain electrons to make that happen? What did sodium do? It gave it. It gave up that electron. Okay? So you're right, it lost them. So if you lose electrons, you are oxidized. So sodium went from a 0 charge to a 1 positive charge. That means it was oxidized. Chloride went from a 0 charge chlorine atom over here to a 1 negative. It had to have gained electrons, so it was reduced. Okay? So you can see how they have to happen in conjunction with one another. You got to have oxidation and reduction together, because otherwise there's no place for it to go, nowhere to give it, that kind of thing. So look at the charges. Okay? Now, it gets more complicated than that, but I'll show you some tricks. Okay? Notice the first giveaway here. Okay, an easy way to spot these reactions is any reaction that has an element that is uncombined on one side and combined on the other side has to be a redox reaction. For example, look how oxygen over here. It's uncombined, right? It's by itself, but on the other side of the equation, it is now combined with something. We don't have enough background to explain, because this doesn't involve charge. This involves a different kind of bonding, so we'll have to hold off as the explanation. But just note that. See how it was uncombined here, now it's combined? That is a redox reaction to make that happen. Something had to have lost, something had to have gained. Same thing here. I went from, on one side, originally it was this, but now I was left with something uncombined on the other side. It was tied up over here, now it's uncombined, redox reaction. Okay? Carbon by itself on this side, over here, made carbon monoxide, so it went from uncombined to combined. This iron went from combined to uncombined, so definitely a redox reaction there. Here, you can look at it from one of two ways. You can look at it from the fact that these are both uncombined. Together, they've created something to combine. Or, you can just realize that from a charge standpoint here, you're dealing with metals and nonmetal. You can look at it charge. This was a 0 charge, went to a 2 positive charge. Had to have lost electrons in order to do that. This went from a 0 charge to a negative charge over here. Had to have gained electrons. So this would have been oxidized. That would have been reduced. To pinpoint down which one would have been what here, you can look at iron. What charge did iron have right here? Look at the charge. Fe2O3, what would have been the charge for iron? Positive 3, right? We reverse these backwards. O2 was the charge of oxygen, 3 was the charge of iron. Okay? Iron went from a 3 positive to what charge? It's neutral. You formed elemental iron is what you did in this reaction. So if you went from a 3 positive to neutral, how would you have done that? You had to gain electrons to make that happen. If you would have lost, you would have become more positive. So iron gained electrons there, so was iron oxidized or reduced in that equation? It was reduced. So you can sort of spot these kind of things and take a look and figure it out. And then this goes with cation changing charge, like we just talked about. Okay, look at it. Cu went from a 1 positive here. Over there it's a 2 positive, right? It had to have lost electrons, so it was oxidized. You can do the same thing down here. This is it's a little more complicated, but it doesn't really matter. You can still figure it out that if you have 2 Cls, what's the charge of 2 Cls together? -2. 2 Fs make what charge? Fluorines are another -2. So together there's a total of a 4 negative charge there, right? So what that 10 had to have been a 4 positive. Okay, so over here it was a 2 positive, and it became a 4 positive over here, so it had to have lost more electrons to do that, so it was oxidized. Okay, how many slides I got left on this? Okay, still got a few minutes. I'm going to boogie on this because I want to try to get as much done as I can. Combustion reactions are easy. You're looking for something that involves a reaction with oxygen, and generally you're going to get some sort of water and usually like a carbon dioxide type product on the end. Okay, you get a lot of energy release from these combustion reactions. You'll find that this is actually a subclass of oxidation reduction is what you get, because you have uncombined oxygen on one side and it gets combined on the other side. So it's actually a subclass of oxidation reduction. But it's so popular and so prevalent that we're going to consider it separately. You'll notice that these are a real pain in the butt to balance. So I promise you'll see one. If you have octane, but break it down, okay? You have octane and oxygen reacting together. This is a gasoline engine. You're going to get carbon dioxide and water. There's also some impurities in there that are going to react. It's going to give you a lot more nasty stuff than just carbon dioxide and water. But if it was pure burn, this is what you would get. Okay, so you would have to balance this, and you would save this until last, right? Because this is if you were balancing this equation, this is a free element. Save it till last. It only affects that. So then you've got hydrogens and carbons. It's probably best if you have a combustion reaction to start with your carbons. Okay, so you got 8 here. You would find that you would start by putting 8 over here. You would see where that takes you. And ultimately what you would do is leave this at the end. You would probably end up with a decimal or a fraction you would have to put in front of this like we did before. Okay? Then you would just clear that fraction from the equation. That's why you get these funky numbers that you see up here. Okay? I'll let you play with that, figure out how that works. It's nothing new. I'm just not teaching you something. So I've already taught you how to do this. It's just some different. You've got to apply it to a little more challenging situation. That's all. Okay, so in this case, notice that I've got C's and H's and O's. Over there, I've just got C's, H's, and O's. I'm always going to get, with the combustion of what's called a hydrocarbon, something that's just carbon and hydrogen, when you react oxygen with it, you're going to get carbon dioxide and water as your products. Okay, and it's usually going to be a bear to balance. Okay. So if your reactant contains carbon, since you're combusting with oxygen, you'll find that what oxygen will do when you react something with it, if you go back, when you react something with oxygen, it will individually bond with pretty much all the elements that you see over here. Okay? For example, carbon and oxygen. Hydrogen and oxygen. If there was something else here, like some other atom, you would see like an S for sulfur. You would also see SO2 over here. You would see that oxygen reacts with sulfur as well. It likes to go in, and it's so strong of pulling stuff apart, oxygen will actually go in and actually usually form a bond with each different atom that's present there. Okay? If it contains carbon, like I said, you'll see CO2. If there's H in that fuel source that you are combusting, you'll find water forms. If there's sulfur, you'll find that sulfur dioxide forms. If there's nitrogen, you'll find that nitrogen monoxide or nitrogen dioxide, both usually form. If it contains a metal, you'll find metal oxide forms. If we were to we skipped this lab, but if you would have taken magnesium metal and you would have supplied a heat source to it and ignited it to combust it with oxygen, a white powder would have flaked and formed. That would have been magnesium oxide. Okay? It would have been MgO in that case. Okay, so so far we've talked about these: precipitation reactions, acid-base reactions, gas evolution reactions, which are usually tied in very closely to acid-base reactions. Oxidation, or what's called redox, we also call them REDOX, redox reactions, and which have a subclass that we just talked about, which is combustion reactions. What you're going to have to do is be able to identify those. I'll have to say, what is this equation? Is this a redox reaction? Is this a gas evolution reaction? Is it both? Is it a combustion reaction? Is it a precipitation reaction? You tell me. Okay, another way to look at this. Okay, don't shake your head. It's good stuff. It's good stuff. You can't go through life and not know this. See, my goal is of all this is I realize that when you leave this class, you're not going to remember most of anything that I've told you. Okay? However, what I do hope that you remember is the world is a lot different place than what most people walk around in it realize. I want you to gain a better appreciation of how this world works at the atomic level and realize the tiny little things that are involved in determining everything that we are and everything that we do. And it happens at such a tiny microscopic level that we take it for granted. And this stuff's happening all around us all the time. Every fraction of a second, all over the place, every possible point in space, this stuff is happening. Okay? And it blows your mind. Wait till I get into how electrons work inside atoms, how they disappear and they reappear. Where do they go? Another universe, another dimension? You laugh, but it's a valid question. Okay? What does it mean to be alive? What does it mean? How do you identify, given that all we are is a bunch of conglomeration of all these types of reactions? That's all we are. What makes us alive? How are we any different than just that reaction by itself, and why is that reaction not considered alive? It's crazy stuff that you have to think about. Okay? I'll fly through this next time we meet.